whatsoever. Oh, recording sounds good. It's no problem. Um, you're good. And my team and I we really believe the ability to communicate is a really important thing about what we do. So we've gotten to work with a professional artist here at Heartwood Visuals to create these general public imagery for some of the work that we're doing. So I just want to make sure to give full credit to Heartwood Visuals when you see the beautiful artwork. So there's a lot of ways that we in this field are using AI to do our science. And I want to touch on a few of those here. So first, using AI for tailored predictions. So let's say a single learning task. We want to predict severe hazard forecasts or create severe weather forecasts in the coming days. On the left is a product coming out from one of my colleagues here at CSU, Russ Schumacher's group, and on the right is the current NOAA product. And currently, actually, this machine learning approach is starting to be used in NOAA operationally. So it's one example. You can think of many where we're using AI for these tailored predictions. Another is AI for post-processing in other ways. For example, doing corrections, compression, or in this case, an example of downscaling weather and climate data to much higher resolution, especially in cases when we think about extremes, especially like precipitation. There's quite a bit of work right now in the field using AI to improve physics-based models. A particular area of focus is what are called physics parameterizations within these climate models. You can think of these as the portion of the climate models that we cannot resolve at that large grid spacing of 100 or 200 kilometers. So instead, what we do is we use simplified statistical relationships to try to mimic these subgrid behaviors. And one big exciting area that emerged for machine learning back in 2018 was, can machine learning help us do this better in our climate models? And there's been a lot of work done and being done on this topic. Another area that I want to particularly emphasize, and I will talk a little bit about in this talk, is the idea of using AI to merge observations and climate model data. For example, we often call this data assimilation in my field, or you can think of it as fine-tuning or transfer learning. But to date, this has been very difficult for us to do. We have our climate model data, we have our different observational data sets, and making the two talk has been quite challenging. And AI is appearing to open new doors to allow us to do this more easily and seamlessly. I already mentioned visualization from terms of graphics, although a real artist, a real human made those graphics, but AI is also being used for climate change communication. So just, humans, we like to think in pictures when possible, and you can go to this website, for example, and look up your address, and it will show you what your house might look like flooded or on fire or in poor air quality. And the whole picture's worth 1,000 words. So different forms of generative AI modeling is being used for that communication. And I would be remiss not to point out specifically deep learning weather and climate emulators and foundation models. So these are purely AI models potentially replacing or augmenting our physics-based models. One example of that is the Pangu weather model that came out a few years ago. Another is the AIFS, the new ECMWF AI model. And then there's Aurora, a new foundation model that's just come out this year, and then others and others and others, and even more, and even more, and more. And this is just a list that we have compiled in the last few days that have come out in 2024. The list is just as long from 2023. So the point is, this is an area that is absolutely exploding, and I will talk on this later in the talk. So why should we even use AI? I know to this group, this is sort of what this, the general topic of mathematics and data-driven methods is all about, but I'm just going to simplify it a bit here and say, well, one reason is to do something faster or cheaper. This is a really important goal. Another is just to do it better. And I think it is useful to think about in which applications are we trying to do which thing, or are we emphasizing? We'd, of course, always like to do it faster, cheaper, and better, of course. But the third one that often maybe isn't talked about as often is to actually learn something new about the system. And that's a focus of my talk today. So here in my group, what we do is we develop and implement AI tools to leverage imperfect data in support of Earth system prediction across time and space. So some of this data or much of this data that we use come from climate models. And I want to point out climate models provide inaccurate, but I would argue invaluable parallel universes that we can mine for information. So we're constantly asking the question, when, where, and how are environmental conditions predictable? And before I go further than that, I want to point out that this is very much a group effort. This is the most recent photo of my group. And so when applicable, I will be highlighting my mentees' contributions and their own work by pink outlines. So when you see the pink, you'll know that this is work being done by one of these wonderful individuals. All right, so for this talk, the way I've framed it is we're going to start at long time scales. We're going to focus on climate change, and then so decades, and then we're going to go down to shorter time scales on multi-year, and then finally we're going to end on weekly Earth system predictions. So let's start on those longer time scales, thinking about how much time we have until certain critical warming thresholds are reached globally. This is an image from the most recent IPCC report. And you can see they're pointing out that as the globe continues to warm, there are these specific thresholds like 1.5 degrees above in pre-industrial levels or 3 degrees above pre-industrial levels. And I want to point out that these thresholds do not have any sort of physical meaning specifically associated with them. It is not some tipping point at this one number, and at 1.49 it won't happen. But they are useful, especially in communicating the types of adverse impacts we're expecting with different amounts of global warming. Now, we can talk about these different levels, but you'll see the question marks at the bottom. And those question marks are because we don't know when the real world may hit those different thresholds. Now, we have climate models that simulate many different climate change scenarios, but if you plot their timing, you'll see they disagree across both time and across the different scenarios. So here are 3 different time series plots, so plotting temperature anomalies on the y-axis for 3 different future climate change scenarios. On the left is sort of a high-end emission scenario. On the right is a much better more mitigation scenario. Each of the colored lines is a different climate model that we are using, and the dashed line shows some of those different thresholds of global warming. And as you will see, even for one particular climate change scenario, for one particular threshold, there's still a wide range of decades across which these different climate models suggest we may hit that threshold. So there's a large amount of uncertainty in that timing. So different groups are approaching this question in different ways, but with my colleagues, we have taken a machine learning approach to try and reduce the uncertainty and constrain that timing. Specifically, what we're doing is we are going to train a neural network to predict how many years until a certain warming threshold has been reached. Specifically, we're going to train on many different climate models, and we're going to give this neural network a map of a specific year's annual mean temperature. So here's an example on the left. And that network is going to predict how many years until that specific world hits a particular threshold. And we know the right answer because we're training on climate models where we know that timing within that climate model. Now, we're not just going to predict just this one deterministic value. We're actually going to predict parameters of a distribution here. In this way, we can actually predict this conditional distribution for that specific set of inputs. All right, so this is the setup. And the first question is, how do we do? Well, when we look at our testing set, so shown in blue dots here, we have true number of years, so our true target or y on the x-axis, and the predicted by our network, sorry, on the x-axis and our predicted on the y. We want these blue dots to follow along that one-to-one line. You'll see it does quite a good job at doing this. And again, this is based on testing data that was withheld from training. Now, this isn't, to be honest, all that exciting. I mean, this sort of one-to-one plot would be amazing, except it's predicting climate model results, which we already know the answer to because we have the data already. What we really want to know is how long do we have in observations, right, in the real world until we hit these different thresholds. So what we can do is we can now input maps or observed maps of annual mean temperature. So you can imagine we have one map from 1980 as shown in the upper left, 1992, all the way to 2021's map on the bottom right. And we can take those maps and push them through our already trained network to predict how many years the observed world has until different thresholds are reached. So we can do this for every year that we have a map, and we can plot how many years we have on the y-axis. Now, this is under a 2-degree warming threshold. So how many years do we have until we hit 2 degrees? Now, a few things. If our network is reliable and good, then we would expect every year we move forward in time, we should be 1 year closer to hitting that threshold under this particular assumed SSP. And indeed, if you look at the last 20 years or so, the slope of that line is approximately -1 years per year. So that's good. But if you're paying close attention, you might be going, well, hold on a second, that slope is not always -1, especially if you go back further. Specifically, you might notice that bump there around 1991. So it turns out that's actually the Mount Pinatubo eruption. What this is telling us is that we already know that when Mount Pinatubo erupted, it released a bunch of aerosols into the stratosphere, which ultimately cooled the globe for the future 2 to 3 years. And in fact, our network was not able to pick up that was an eruption, but rather said, hey, look, the globe is cooler, and so we must be further away from that 2-degree threshold. It wasn't until after those impacts or those effects of the eruption went away that finally the network was back on track for this -1 to 1. So we've done this for our different SSPs or our different future climate scenarios, and we can then make predictions with our network of how many years we have until this 2-degree threshold is reached under these different climate change scenarios. Again, incorporating this uncertainty through this predicted conditional distribution. And we can talk about the width of that and the uncertainty in that distribution, as well as when it thinks we will hit this 2-degree threshold and under certain assumptions. But I think my main point here is that what made this approach a bit different is we found a higher likelihood of reaching 2 degrees under this low mitigation scenario than some previous assessments did, using this both climate model training, but then applying it to observational approach. So this is a global picture, right? When will the global mean hit certain thresholds? But that global mean is made up of many regional temperature anomalies. And so our most recent work, which will just come out, I believe, next week in Environmental Research Letters, further takes this approach and refines it regionally. So as an example, let's focus on Central North America. That's where I am right now, here in Colorado. I've already shown you how we can train on climate model data and then use it to predict observations. But now what we're going to do is we're going to do something a little bit fancier. We're going to train on climate model data and then fine tune with the limited observations that we have to date over this region. For example, this region of Central North America has already warmed quite a bit. And so we can use that to further fine tune the network to the truth, to the observations, rather than just learning from climate models alone. The hope being we will get a better prediction than we would have if we trained on climate models by themselves. So we can do this and we can end up, based on this approach, which I won't go into too much detail, we can end up creating predicted time series of Central North American temperatures in the coming years. And specifically with temperature anomaly is on the Y, all those gray spaghetti lines in the background, those are the different climate model predictions or projections, I should say. And you see that large spread in what the future may hold over Central North America. The black line is what we've seen to date in terms of observations. The green base network is that network that was trained on climate models alone. And we can see it doesn't align quite as well as we'd like with the observations. But with a small amount of fine tuning on observations to date, we see that the orange curve is a much better prediction for the past, and that's potentially also for the future. Now, we have done this for more than just Central North America. We've actually done it for all of the IPCC regions. And you can go and look at, your specific region of interest. The take-home point, though, here is that, most land regions we find will likely surpass that critical 1.5 degree threshold by 2040 or earlier. And our approach not only constrains that gray bounds of climate model projections, that is, makes it narrower, but it also tends to make it earlier. And this fine tuning further makes it narrower as well. And I will point out that in doing this, several regions are on track to exceed 3 degrees by 2060 as well, which is sooner than anticipated in earlier studies. All right, so we've used machine learning. We can make some predictions, potentially constrain our climate model projections a bit better than we could otherwise. But how did the network make this prediction? Especially in the case I just showed you, during this fine-tuning step, how did the network update its weights and biases to make a better prediction of the real world? So what if we could learn which regions of the globe were the most relevant for improving this prediction with observations? And this is where explainable AI comes in. So this concept of opening the black box. Now, explainable AI has been a huge field of research in computer science for, I would say, at least a decade now. However, there are now resources and papers out there specifically using, providing an overview of explainable AI for the geosciences. So for those of you interested in jumping in who have more of that geoscience background, these could be a good place to start. So there are many explainability methods out there. I'm not going to discuss them all in detail, but I will highlight one that I find particularly advantageous for doing climate model or climate research. Specifically, we have found the form of XAI known as attribution heat maps to be particularly useful because they are largely consistent with how many Earth scientists pose their questions. And just as a quick example of how these tend to work, imagine you've already trained a neural network to do some sort of image classification task. And in this case, you put in an image of a cat and you want to know the probability of there being a cat, and then the network outputs a 0.8. And you might ask the question, where does this 0.8 come from, right? Why 0.8? Well, many of these attribution methods take that 0.8 and propagate it back through the network, providing one with a heat map of the same dimensions and size as the input, where that heat map shows the most relevant regions for that 0.8 prediction. And when it's a conservative method or XAI method, you can add up all those red pixels on that heat map and they should ultimately sum to 0.8. So this allows us to start to get a feeling for the regions that the network found most important for its final prediction. Now, why should we care about XAI? And for many of us who are scientists or in the pursuit of knowledge, we typically are always wanting to know why. And so it might be sort of obvious that we would want explainable AI. But I have had many interactions with folks who are not, do not have that background. And they just say, I just want the best prediction possible. I don't really care why. But I argue they should still care about explainable AI. And the first and foremost reason is we need to gauge trust in these networks. And one of the main reasons humans gain trust in using different tools is understanding how they work and understanding why they are doing what they are doing. And explainable AI is very helpful for that. Another reason that goes along with gauging trust is if we find something that the network is doing that doesn't lend us to trusting it, we might be able to fine tune and further optimize the network via changing its architecture or its loss function to allow us to make predictions in a way that we find more trustworthy and potentially are an improvement. And then finally, we can also use explainable AI methods to learn something new about our system. And our ultimate goal is to understand causality. I want to be clear, however, that XAI does not give us this, right? At the end of the day, this is still what we are doing is still correlation, not causation. But I would argue explainable AI is still a step in the right direction. So taking these tools and methods, these explainable AI tools, can we apply them to our case of climate temperature constraints over Central North America? So if you remember, we're predicting how many years we have until Central North America hits different climate thresholds. And when we fine-tuned with the observations, our network improved substantially and was a better fit for observations. So we can use explainable AI to create heat maps of the network's predictions for both that base network and that updated or fine-tuned network and take their difference. That is, this is the regions of the globe where XAI, in this case, it's deep SHAP for those curious, so shapely values. This tells us the regions of the globe that were most relevant for that fine-tuning, that update via the observations. And in the end, these regions end up pointing towards regions with relevant climate model biases for our particular prediction. So in this case, it's really highlighting the Southern Ocean as well as regions over Central Asia. Now, when we think about climate change in these long timescales, we largely expect to see warming. And the question we've been asking is, how fast of warming do we see? That is, if we run many different climate model simulations and we ask the question, what do the temperature trends look like over the next 30 years? We see red mostly everywhere. And actually, this is not a bunch of different climate model simulations. This is the same climate model with exactly the same inputs and forcings run 100 times. The only difference between these different 100, what we call ensemble members or storylines or trajectories, is that back in 1850, when at the start of these simulations, the surface temperature was, noise was added to the surface temperature at the value of 10 to the minus 14 Kelvin. And I want to repeat that because people sometimes think I misspoke. So that's 10 to the minus 14 Kelvin noise is added to these different surface temperature maps. This is tiny. However, due to chaos, that these initial differences grow and provide us with very different patterns and trajectories of climate variability over the coming decades. But in all cases, we see warming over most of the Western US and in fact over the globe because they all share similar climate forcings. However, this is over a 30-year period. If instead you just take a 10-year trend from these exact simulations, you get very different answers depending on which little square you look at. What that tells us is depending on which world we live in, we could actually experience cooling over the next 10 years that is completely consistent with a forced climate change scenario. It's just climate variability that is sort of the noise inherent within the climate system can play a dominant role in that variance. That is, natural variability is much larger than the climate change signal on regional scales and can confound our knowledge of what the future holds. It can be helpful to look at this in a slightly different way. So instead of 100 maps, we can plot 100 lines or time series for a particular region. So this is over Chicago, Illinois, so another central US grid point. 100 different lines showing 100 different possible futures as simulated by one single climate model. Now, a few things you notice, if you take the average, we often call this in our field the forced response. That's sort of that average response we expect from this climate change forcing. You'll see wiggles are still present, and actually those are not noise. The majority of those are actually small volcanoes going off across the globe. And already I've talked about how we are trying to understand and predict this forced response. However, we don't live in a mean world. We're going to live in one of these 100 or however many you have ensemble members. We could live in number 40, and this could be the world we look at, what our world looks like, or we could live in number 32. And so in that sense, we're using AI, as I've already shown, to leverage imperfect climate models to constrain future projections, fusing simulations and observations. However, we're doing more. We think about shorter time scales as well. For example, within this number 32, we could ask questions like, could we predict the rapid cooling that occurs over the next 30 years in this one simulation at this one grid point, so over Chicago? And why might we want to actually predict this natural variability in this behavior? Well, for one reason, to prepare for weather and climate hazards. However, there's another reason that I think is going to start showing up more and more with more and more importance in the next few years, which is being able to predict this type of daily to yearly variability will become important for anticipating the masking of the intended effects of climate policies. That is, if certain climate policies are enacted and the globe warms even faster than it ever had, there could be implications for society thinking it's not working, when in fact it could be that natural variability just wasn't, if you will, on our side. So one big goal of our group is to try and predict these sorts of fluctuations in the coming days to years. Sounds sort of easy, but just to point out, if you don't know already, climate prediction is incredibly challenging. We cannot expect to make perfect predictions all of the time. And I actually find this really interesting about our field compared to many of the other AI applications in the industry. That is, we are not actually trying to make perfect predictions. We just want to look for specific states of the Earth system that lead to enhanced predictable behavior. That is, we often call these state-dependent predictability or forecasts of opportunity. And AI can help with this. From a more simple picture form, imagine an XY plot where 80% of the data is noise in some ball in some corner of this quadrant, but only 20% of the data falls along some nice clean line. It could be that if we train our AI models to try and predict perfectly everywhere for everything, we could be hampering our ability to learn these specific predictable behavior, cases. And some examples of what I mean by that predictable behavior, there are different oscillations or phenomena within the climate system that lend to more predictable behavior than others. For example, here are two climate phenomena that originate in the tropics that are very important for this state-dependent predictability. For example, you may have heard of ENSO, or the El Nino Southern Oscillation. That can give us predictable behavior on timescales of 1 to 2 years or so, or on shorter timescales, the Madden-Julian Oscillation, which can give us information about what the weather will be in the coming weeks. So let's focus first on these longer timescales. So thinking about the El Nino Southern Oscillation, so 2 years or so into the future. So members of the group set up a network to predict ocean temperatures in the coming 5 years at a particular grid point. So you can think about this as, what will the temperatures look like in the coming few years? To do this, they put in maps of sea surface temperatures from the past to give it information about both the state of the climate as well as its time tendencies. And the goal is to predict or classify the temperature anomalies at a certain grid point in the coming 5 years, whether they'll be warmer than average, sort of average or neutral, or cooler than average. So we've done this. We've done this for every grid point of the globe, and we can make a plot of accuracy of how well our network does at making these predictions. We get a plot that looks something like this. So this network was trained on 3,630 years of climate model data, which we of course do not have in the real world, that amount of data. And every grid point shows how accurate this approach is for that grid point, where the way we've set up the classification task is random chance is about 33%. And if I had an audience here, I think I'd see a lot of raised eyebrows of, this looks a lot like noise or random chance. And I completely agree. It all looks sort of like that yellow banana color, which is pretty much just random. So this is one of the reasons the field for a long time has been saying this is an impossible problem. But if instead we don't say we're not trying to predict everywhere, instead, let's focus on when the network says it's going to be most accurate. That is, when the network is most confident in its predictions. So this is the 40% most confident predictions as quantified by the neural network. And suddenly we start to see some patterns emerging. If we go even further and we look at the 20% most confident predictions, we find regions of the globe with high accuracy, or much higher accuracy than random chance. And so what this is saying is, when the network is confident in its predictions, that is, it has identified state-dependent predictability, we tend to be more accurate as well. Now, this was all on climate model data and testing. These results are for testing data from that same climate model. But what about the observations? So in this case, we've trained the network on that climate model, and now we're just going to push the observations through and see how it does. Now, for the observations, we only have maximum about 169 years of data. But still, on that testing set, on the left, if we evaluate all predictions, it looks pretty dismal. But as we look at when the network is confident in its predictions, we find that we do better for observations as well. So this is for one climate model, but one of the things that has been really exciting about this approach is it gives us a framework to compare many climate models to each other. And I'm not going to go into all the details, but I just want to point out that this is a different map for networks trained on different climate models. And the point is, we can start to compare them compare their sources of predictability where they're skillful in terms of trying to understand which climate models may or may not be best for predicting the real world. All right, so what does explainable AI have to do with this? Well, you may be wondering from all these red blobs, especially say over the North Atlantic or over the Pacific, where is that source of predictability coming from? Why is there state-dependent predictability in the climate system? And put another way, which regions of the globe were most relevant for these state-dependent predictions? Once again, this is where XAI can come in. It can help us learn something new. So this is a very similar task, predicting 5-year temperature, but in this case, we're going to predict land temperature in the coming years. And again, using climate model data. In this case, we're going to predict whether it's colder than average or warmer than average. So it's binary. Once we've made that prediction, we can then use XAI to ask which regions of the input of the sea surface temperatures were most important for that prediction. And these are those heat maps that I've already talked about, if you will. They're a little more interesting than the cat, okay? Showing the most relevant regions for predictions of temperature over Mexico, California, the Midwest, and Canada in the coming 5 years. So one important thing to note is that the network is able to learn different sources of predictability depending on the region it's predicting for. And that all 4 of these different patterns are something that as a climate scientist, we somewhat expected to see somewhere on the globe. For example, the Kuroshio extension for Mexico, we see that also for the California prediction. And then we see the North Atlantic popping out as also an important source of predictability for California and Canada. And then the Midwest, really a focus on that ENSO or that El Nino region. Now, this is for different predictions in different locations, but what about predictions for the same location? So let's say we're just going to focus on making predictions for the West Coast of the US. Because of the nonlinear interactions within this neural network, it can learn different patterns or different sources of predictability depending on what the climate system looks like at the time. For example, the Kuroshio extension is important in about 42% of the samples, whereas the North Atlantic pops out as important for 34% of the samples. And then the bottom case is what we call the Pacific Decadal Oscillation, or the PDO, which is yet another pattern of climate variability that is sometimes, that is under certain states, important for predictability along the West Coast. All right, so we've used AI to explore Earth system predictability again on these longer time scales, so years in advance, but we can also focus even closer on what we call subseasonal to seasonal prediction. So when we think about making predictions of the coming weeks to months. And we've done, with similar approach. Now, I will point out, actually, this is an area that my group does a lot of work in, and I could give you lots of slides that show you lots of heat maps and things like I've shown already. But instead, I want to focus on sort of where the field is right now, and that is the fact that these AI weather or digital twins have arrived. So these models have just exploded, these pure AI models for weather prediction over the last 2 years. On the left here is the SFNO, or the Spherical Fourier Neural Operator model and architecture. This is called ForecastNet, which is out of NVIDIA. And on the right is the Ground Truth. Now you can't really do much comparison other than see, wow, they both look beautiful. And that already is impressive, but we'll get a bit more quantitative here in a second. Now, my group's really interested in subseasonal timescales, but right now these models really are showing their power in the weather timescale. So you can think out a few days to maybe a week. And just over the last few years, we've seen many of these models appear and accelerating improvements since 2019, such that the most recent set of models are said to potentially surpass our current physics-based models. But as I already mentioned, while the weather timescales are really, these models are really dominating on the weather timescales, we are starting to see the emergence of pure AI models for timescales beyond weather. That is, for example, Neural GCM, a model I really like out of Google, is starting to think about subseasonal to seasonal forecasting, so these longer timescales. One of the neat things about Neural GCM, I won't go into details unless there's questions, but they've actually built a hybrid model where there's a dynamical core with Navier-Stokes, the old-fashioned way, but then a second component that does all of the learned physics. You can think about it as the thermodynamics, as well as the moisture processes, et cetera. And coupled together, they create a forecast. So how are we using XAI for subseasonal prediction with these AI models that are just coming online for these timescales? Well, we're really leveraging XAI to assess the sources of prediction skill within these models. That is to try and understand what they're doing. I've already mentioned that we know the Madden-Julian oscillation, which is this oscillation of this convective system. So the green blob in this little video moving from west to east on these 30 to 60 day timescales. This pattern can excite what we call Rossby waves, which propagate into the mid-latitudes and can impact weather, in the US, but also Europe, Asia, et cetera. So what we've done to try to better understand how these AI models are simulating this is we've actually taken something out of good old-fashioned idealized climate modeling experiments, which is we're perturbing the model in a very idealized, simplistic way. In this case, we're putting in an additional source of heating in the tropics to sort of mimic this Madden-Julian oscillation phenomena. What we expect to see is in the coming days, a wave train to appear over the mid-latitudes. And we know from our idealized physics-based models that this is in fact what happens. The question is, what do the AI models do? And when we do this sort of idealized experiment, we see here on the right is the result of the circulation in one of these AI models in the coming weeks, where we see this high-low wave train pattern, which is actually quite similar to what we expect, suggesting that these models are indeed learning physics-based responses. Now, why might you care about this pattern? I said that this pattern of circulation can impact the weather. Well, one way it can impact the weather is by setting up high pressure systems, which can block the jet stream and the storm tracks and lead to extreme heat in the coming weeks. So this is the specific example, the June 2021 North Pacific heat wave here over the US. And Kelsey and my group is going and evaluating the extent to which these AI models can forecast these sorts of events on these weekly timescales. So in this case, we're looking 10 to 20 days in advance. And we see in some cases, for example, the AI GraphCast model out of Google, it does quite a good job at simulating that heat wave on subseasonal forecasts, on subseasonal lead times. But other models, for example, in this specific case, the Pangu AI model really seemed to miss that heat wave onset. So we're moving further and just generally talking about the need to evaluate the utility of these AI models for a wide range of extremes, not just heat waves. So unlike weather forecasting models, Earth system models, if we're going to talk about subseasonal to climate timescales, these sorts of Earth system models must remain credible when external conditions are different from history. That is, things like CO2 levels are changing, because we know that's what we're expecting in the coming years. So we are using and running a few of these different AI climate models. In this case, this is called the ACE model, to simulate extremes, in this case, extreme hurricanes under a range of different climates to see how they perform. And so in this way, we really need to continue to conduct thorough and independent evaluations of these AI models. Now, once we've done that, we can maybe start to think about longer timescales. So when pure AI models see something that physics-based models don't, maybe we can use them to improve those physics-based models, including our climate models. For example, we're exploring the use of AI for understanding the sensitivity of the top of atmosphere radiative imbalance driven by sea surface temperature warming. And we're finding from these results that while some AI models struggle to replicate these relationships seen in the physics-based models, so the right shows the physics-based model sensitivity and the left shows the AI model, others are doing an excellent job. And in fact, this particular AI model, while the values are muted, the sensitivity pattern is actually very similar, which was very surprising to us, actually. It's much better than we thought. And we're even finding further that we see more fine scale structure in the AI model that we think is real. So further allowing us to maybe improve our physics-based models in addition. And finally, I do want to point out, I think these are early days, especially for AI climate models, but we need to put as a community a lot more deep thought into how do we improve these AI climate models if they fall short. We know for our physics-based models, we have ideas for how to improve them, but how do we do that with the AI models? And then of course, how can we leverage their power if they succeed? And as I've just discussed, a major impediment to using these models is their black box nature. And to be clear, explainable AI is great. It's in my title. But I will point out that it is applied post hoc and can still be hard to interpret on its own. For this reason, my group is also exploring what we call interpretable AI, or methods that are interpretable by design, mimicking scientific human reasoning to improve intrinsic interpretability. For example, we're building models that have forms of interpretable soft attention to make predictions like a climate scientist might, focusing specifically on different parts of the globe to ultimately make its prediction and be understandable while it is doing it. And having interpretability doesn't necessarily mean a lack of skill. So we are using these interpretable methods now to constrain model projections and turn them into initialized predictions. So again, constrain our full climate model range to try and reduce that uncertainty to something narrower. All right, so in my final few minutes, I mentioned that this already is complicated. The Earth system is complicated to predict, but let's not forget it is coupled and further complex. Human development and environmental factors cannot be easily decoupled. And so one question is, how might we responsibly harness AI to anticipate this coupled system and support a thriving society? And so in my final minutes, I just want to talk about a few ways we're starting to approach these questions with explainable and interpretable AI. So as I've already mentioned, climate variability can drive climate extremes, and compound climate hazards in one location can impact other locations across the globe. That is, what happens in one location can be transmitted globally via social telecouplings, for example, international trade. This means that anticipating exposure to these compound climate hazards is a complex combination of both the climate and the social teleconnections. So we are studying this by looking at the trade of calories across the globe and trying to understand how that trade is impacted by climate hazards in one location impacting other regions and their food. So one question is, can we anticipate these worst case scenarios? So we've done work now looking at how much of the caloric supply is exposed to different climate hazards for different countries around the globe, which again is this mix of both the climate variability and their trade patterns. So the devastating impacts of climate change can obviously further exacerbate these extremes and worst case scenarios, and motivated by the fact that global warming will continue over the coming decades and by the uncertainty in future global mitigation efforts, research on climate intervention is gaining more attention, or also sometimes known as geoengineering. So I would argue that adopting an interdisciplinary approach is essential for gaining a clearer understanding of the potential future benefits and risks of such an approach. So in our group, we are leveraging explainable AI to analyze data from climate model simulations of different climate intervention scenarios. And many of those simulations have been done using what we call collective actor scenarios, where we assume the world has come together to agree to geoengineer the planet, and we all agree this is the way to do it. And we have papers using explainable AI exploring those different worlds and the impacts on the Earth system. However, you might be thinking, well, that sounds, everybody coming together and agreeing is already very hard. What about these alternative scenarios, which we call rogue actor scenarios? And actually recently, just last year, there's a congressionally mandated report on solar radiation modification that specifically highlighted the urgency around assessing the outcomes of these unilateral or rogue actor simulations. So we are currently using explainable AI to explore the impacts under these different scenarios, as well as simulate these scenarios in AI climate models. But humans are impacting the Earth system by more than just modifying the atmospheric composition and radiative balance. And I want to finally end my talk here highlighting some work we're doing, thinking about the footprint of humans on the land surface and how that's been impacting ecosystems, both in the past and as expected for many years to come. So to address how human development has been and will continue to be modified by climate hazards remains an open question. And in fact, in the ecology and biodiversity community, they rely heavily on something called what's called the Human Footprint Index, which is this number quantifying how much humans are impacting the land surface at that location. Now, this is an incredibly difficult quantity to come up with at high resolution, and it often lags about 7 years from real time. That is, it takes about 7 years to collect all of the data and paperwork necessary to come up with this one number. Where you can think of a 1 as being a shopping center parking lot, and a 0 being, say, maybe a pristine forest. So what we've done is we've taken this hard work of this community where they've, in essence, created a labeled data set, and instead are training AI to take in Landsat imagery to predict this quantity, which ends up being a much easier thing to do in terms of, is easier in terms of speed for sure. So that is, we take in Landsat imagery, for example, from 2019, and then predict this quantity. And in doing so, we can create maps from the year 2000, for example, of this Human Footprint Index, and a map, say, from 2019. And in doing so, we can compare the two and ask questions about how the Human Footprint Index has changed over the last few decades. Specifically, we can also use explainable AI, again, to gauge trust and understand how the network is coming to its prediction. This is a favorite example of mine, where in 2019, the Human Footprint Index was predicted to have doubled, and XAI shows us that the main reason for this is the AI pointing out that a new highway went in over those years. And in fact, this is the Trans-Sumatran Highway that went in 2019. Furthermore, we've used XAI to help us choose which Landsat channels are most beneficial for this prediction task, thus allowing us to fine-tune and optimize our approach. So we already have a paper looking at this, comparing 2019 to 2000, and again, using XAI to highlight the decision-making process of our algorithm. However, we've now extended it to higher resolutions at both space and time, where we now have imagery from every year from 1998 to the present day. And one of the big questions we're asking is, can we use this data set to quantify the present and predict the future of human development and migration under climate hazards? That is, how has and will human development be modified by different climate hazards across the globe? And this is work ongoing. All right, so I will wrap up and argue that the future of AI for Earth systems science requires and will require interdisciplinary thinking. And ultimately, we want more than just a prediction. We're going to want to know why. So thank you, and I will take any questions.
Thank you very much, Libby, for this very interesting talk. I don't see any questions in the chat box yet, but everybody just feel free to also just raise your hand or just freely ask your question if you have any. Right, there's one from Huang Yu, which I'm going to read to you. Thank you a lot, Libby. Deep learning for climate projection is very promising, but people often doubt if deep learning can well address the out-of-sample predictions for the unseen future climate. I'm wondering if you have any good idea about this issue, or in what extent we can trust the deep learning for climate projection.
Yeah, so this is a great question, and something that the field, one, as a scientist, we sit here going, oh, yay, something for us to do, right? Like, this is good. This is physics. And as I mentioned already, the weather timescale, and one of the reasons I think that AI weather models have exploded is we don't really have to worry about this question as much. We're thinking about predictions in the next 7 days, not in the next 70 years, right? And as we go on to these longer time scales, suddenly what we're stating is our AI model needs to be able to do out of sample or extrapolate, right, in a way that it's never seen before. And so, as I hope I highlighted in parts of my talk, this is where I think climate model data and its importance is not going to go away. Now, climate models themselves are not perfect, but they do encapsulate a lot of the known physics that we know should not change between now and, 2050. They have Navier-Stokes. They have, the thermodynamic set of equations. They have the physics that we understand to date. And as long as the physics doesn't change, that could be a good training set. Now, the climate models themselves have known issues that are, some of them, incredibly difficult to tackle, that have been known for decades and we still haven't made progress. And that's where I'm arguing that I think training this deep learning, both on climate models, but fine-tuning with the limited observations we have, may be a major way forward. Other approaches are hybrid models, like I mentioned, neural GCM, where they try to put the physics we do know in them as physical equations, and then augment with AI sort of, sorry, the word physics is used in funny ways in our field. Try to use the AI-based, we'll say, convective properties and thermodynamic and moisture properties or phenomena within the system is another approach. However, I will point out Neural GCM has also talked about, can we train on more than just the observed record? Can we also train on climate model data? So I think this is going to be, this multifaceted approach will be the way we get at this very important problem.
Thank you. Very interesting. I'd have a few follow-up questions, but I should rather go through the list of questions that the audience asked. So the next one is lovely talk. I agree. How do you estimate probabilities and evaluate how they are related to the dynamics?
Okay, so I can start with the first one, and I think the second part is more vague in general. So in terms of uncertainty quantification or probabilities, this is right now a big area of research. So for those interested in going into this, I would argue this is a great place to start, especially if this is more of a math statistics community. There are a lot of different ways people are using deep learning to estimate probabilities, and I think all of them are flawed in their own ways. And so understanding the benefits and downsides to each for specifically Earth system prediction is a huge unknown. Sorry, I sort of made a pun there, an unknown of unknowns. But a lot of work being done in the computer science community about what the unknowns and downsides are to these different approaches for things like image classification, large language models, et cetera. But I think that's fundamentally different than the physical Earth system. And so that's a big area of research. In our work, for example, we've taken an incredibly simplistic approach, and we are training deep learning models to predict the parameters of a bunch of conditional distributions. We are also training it, I haven't shown this work, to predict large ensembles, so many deterministic values, which can ultimately give us some sort of PDF of uncertainty. A big part of that is how we write the loss function to really decide how we want to train to predict those probabilities. So I've kept it vague here, but there are lots of ways that people are approaching this. And how they are related to the dynamics. Again, I think this is where we can draw from climate model approaches from the decades of the past and start to explore what were the states of the system prior to, say, large uncertainty or smaller uncertainties, and really start to pull at what phenomena are driving those probabilities and those distributions.
Great. Thank you, Libby. The next question. What known climate phenomenon became visible in the more accurate predictions? I know you mentioned the ENSO and NAO. Anything more specific, and what did the models get quite wrong?
Oof. Okay. I mean, so we've seen lots. We've seen ENSO, NAO, Pacific Decadal Oscillation. It's typical. I call it alphabet soup within the climate community. In one project, we've actually found a source of predictability that was quite robust in a region we didn't expect. So it was looking at subseasonal forecasts, and it was a region really near Hawaii. And it turned out that we think what that is it's really, for those of you who are on the climate dynamics side of things. We think that was picking up the Rossby wave source at the flank of the subtropical jet that allowed the excitation of the Rossby wave throughout the mid-latitudes, because ultimately we were predicting mid-latitude circulation. So that was exciting, because then that suggests that maybe we don't need a neural network at all. Now that we know that location, maybe we can create some sort of index or yet another alphabet soup to maybe make predictions in a much more interpretable way. So that was exciting. In terms of what the models get quite wrong, they get many things quite wrong. I'm not sure I could, one region that I think is going to sound boring to this audience, but I think it's worth emphasizing again, is the desire of these data-driven or deep learning models to regress to the mean or to go to climatology, right? And so a big amount of effort that we do goes into making sure that it can't get a good accuracy or a good prediction for all the boring reasons, like learning the summer's hotter than the winter, or that it rains during the rainy season and doesn't rain during the dry season. That kind of the amount of effort that goes into that pre-processing to ensure that the network's actually learning the things we don't know is incredibly important. And if we don't do that right, it gets a lot of things wrong.
Yeah. Next question, and we're sort of late-ish already, but let's go through them. You showed some nice examples of AI finding known physical patterns that explain climate connections. Can you also give us some examples where AI found a physical pattern that wasn't known beforehand, but was found to be physical and not spurious? I think you just gave a good example of that.
Yep, I gave one example, and another example I will just point out is on long time scales when we're thinking about the relationship between sea surface temperature warming patterns, say due to global warming, and what's going on at the radiative, imbalance at the top of the atmosphere. This is early days, but the AI model kept picking up on much finer, detailed structures over the oceans than we were typically getting with our typical Green's function approach with the climate models. And at first we thought it was just noise, but we're running now physics-based model simulations, and those fine scale structures appear to maybe real. And so this is another example where we actually thought it was wrong and went to prove it, and we're finding maybe it's better than we thought. So that's a positive story about the non-failure of these approaches. Yeah.
Very interesting. Although, then for the final question, I'm wondering about training AI models in the climate world and applying to observations. In the climate model world and applying to observations, sorry. Two parts to this question. Without transfer learning, in the SST example, do you need to bias correct, or can we trust the results as they are? B, with the transfer learning, you got to a map pointing at relevant climate biases with explainable AI. Have you thought about whether such an approach could even be used for bias correction?
Great. All right, so for question A, so without transfer learning, do you need to bias correct? I am certain bias correcting won't hurt if we're doing it well. We did not bias correct. However, I want to go back to my point about pre-processing. We always input maps of anomalies. That is a different, deviations from some baseline period within that same data set. And that's because different climate models and the observations sort of all start from different places. They actually have different just mean temperatures. And if we didn't do that, we'd actually get very boring results. And then AI would just tell us which models were too cold and which models are too hot. So already in our pre-processing, we are in a way bias correcting to a certain extent to put everybody on the same playing field to try and again learn something we didn't know and couldn't have done before. So that's answer to question A. And then B, with transfer learning, we got this map that actually points to relevant climate biases. Now, I will point out, if we just look at climate model biases generally, assuming we have an observational data set that we believe is close enough to what reality is, we can compute these mean biases very easily. So it's not taking averages and subtracting them. No AI necessary. I think what is interesting about the map I showed is it's not just showing us the biases everywhere. It's showing us the regions the biases matter for this task. And so, yes, to a certain extent, it could be used for bias correction. But I think, I'd sort of prefer to just bias correct everywhere. And so I think I'm not sure I would take that map straight out of the box, but it does suggest maybe those are regions we need better observations. Those are regions that we need to focus a bit more on the physics. However, I will point out that's been really hard, for decades. So just knowing that the bias is there does not mean we can fix it. And so I think I may have made it sound a little too easy, but I do think that these maps are at least starting to point at the regions that maybe we should put special focus on for specific climate problems.
Great. All right. Let's end there. Thank you so much, Libby.
Thank you so much for the invite.
And thank you for the very clear answers to all the questions. Thanks to the audience for asking really great questions, I think. All right, so everybody stay tuned. We're gonna take a little winter break of a few months, but we'll be back. You'll receive the emails if you're on the list. And with that, have a lovely rest of the week. Have a good day, those who are, or like a good evening, wherever you are. And thanks, Libby, again. Take care.
Yes, thank you. Thank you, everybody. Bye.
Bye.